Welcome back. At first, Happy Republic Day. Wishing you a day filled with pride, honor, and love for our country. Let's take a moment to grateful for our gift of freedom and commit to building a stronger, progressive India. Today I will see some properties of reducible and irreducible polynomial. First property, if fx is irreducible in Q, then is it irreducible in Z? Means integer. That means if fx is irreducible in rational number, then is it imply it is irreducible in integer? This question is very important. At first, I will tell you, just think oneself, then see my solution. This, consider fx equal to 4 plus 2x square. We can write 4 plus 2x square as 2 times 2 plus x square. Now consider this is gx and this is hx. Notice gx equal to 2 and hx equal to 2 plus x square. That means the function fx can be written as product of two polynomial gx times hx. And here we all of us know 2 is a unit in Q. And since 2 is a unit in Q, so that implies fx is irreducible in Q. We all of us know in Z only unit is 1 and minus 1. In Z, this polynomial is not irreducible, only irreducible in Q. I hope my all viewers have understood. That means if fx is irreducible in Q, that does not always imply this is irreducible in integer. As for example, consider the polynomial fx equal to 6x square plus x minus 2. Is this polynomial is irreducible over Q? Check it. Notice this polynomial we can write 6x square plus 4x minus 3x minus 2, which is equal to 2x times 3x plus 2 minus 1 3x plus 2. That means this is 2x minus 1 times 3x plus 2. That means here the root are x equal to half and x equal to 3 over 2. And half and 3 over 2 always belongs to Q. Since the root belongs to Q, that means this is not irreducible in Q. That means this is reducible over Q. And since reducible over Q, that means this is reducible over integer. I hope my all viewers have understood the question easily. Okay? Oh well. Now I will see when irreducible in Q imply irreducible in Z. For this, I will see what is the definition of primitive polynomial. The content of non-zero polynomial a(n)xn plus a(n minus 1 xn minus 1 up to a0. If the greatest common divisor of the coefficient of this polynomial is 1, then we can tell primitive polynomial is an element with content 1. As for example, consider the polynomial 2 plus 3x plus 9x square. Notice GCD of 2, 3, 9 equal to 1. Since GCD of 2, 3, 9 equal to 1, that means obviously this polynomial is primitive polynomial. And when the polynomial is primitive, then irreducibility in Q always imply irreducibility in Z. Okay? Now I will see irreducibility of Q always imply irreducibility of real number. This is not always true. For this, consider fx equal to x square minus 2. This is means obviously x minus square root of 2, x plus square root of 2. Obviously, root 2 does not belongs to Q, so we cannot factor in Q. So, in Q, fx is obviously irreducible. But since the root belongs to in R, since square root of 2 belongs to R, so we can tell this fx is reducible over R but not Q. I hope my all viewers have understood. That means irreducibility of rational number does not imply irreducibility of real number. Similarly, irreducibility of real number does not always imply irreducibility of complex number. As for example, consider fx equal to x square plus 1. We can write this is as x plus I times x minus I. Obviously, I belongs to complex number. So, we can reduce this is in complex number, but this polynomial is irreducible in real number because in real number it has no root. We cannot factor this is in real number. So irreducibility of real number does not always imply irreducibility of complex number. Now I have seen irreducible over Q does not always imply irreducible over Z. But if fx in Zx and fx is irreducible over Z, then that implies fx is always irreducible over one example which had come CSR Net June 2016 exam. The example is if fx in Zx be a polynomial of degree greater than equal to 2, then pick each correct statement from below. If fx is irreducible in Zx, then it is irreducible in Qx. 2. If fx is irreducible in Qx, then it is irreducible in Zx. 3. If fx is irreducible in Zx, then for all prime p, the reduction fx of fx modulo p is irreducible in fpx. 4. If fx is irreducible in Zx, then it is irreducible in Rx. Option 1, option 2 and option 4 obviously true, because few minutes ago I have discussed this part elaborately. Now I will see option 3. If fx is irreducible in Zx, then for all prime p, the reduction of fx modulo p is irreducible in fpx. Consider fx equal to x cube plus 2x square plus 2. Obviously, GCD of this polynomial 1, 2, 2, obviously this GCD would be 1. So, by Gauss lemma we can tell if fx is irreducible in Q, then that always implies, since the polynomial is primitive polynomials, that always imply fx is irreducible in Zx. Now, and by Eisentian criteria, for the prime p equal to 2, we can tell obviously this polynomial is irreducible in Q, and since this is irreducible in Q, that implies this is obviously irreducible in ZX also. And here the question, if fx is irreducible in ZX, then for all prime p, the reduction of fx is irreducible in fpx obviously. Consider also p equal to 2. Then obviously f bar x would be x cube, and we all of us know f bar 0 equal to 0. So this is irreducible in Q, but not, this is irreducible in Z2x. So option 3 is a wrong option. I hope my all viewers have understood. If fx is irreducible in Zx, then for all prime p, the reduction fx modulo p is irreducible in fpx. Okay? OL. My next example, some result about Eisentian criteria. We all of us know what is the Eisentian criteria. Let fx be the polynomial a0 plus a1x plus a2x square up to an minus 1 x to the power n plus an x to the power n, which is belongs to integer n, if there exists a prime p such that p divide a0, p divide a1, p divide a2 up to p divide an minus 1, but p does not divide an and p square does not divide a0, then we can tell the polynomial fx is irreducible over rational number. And there exists some result about this criteria. The result is, let f be a field and consider one non-zero element a belongs to f. Then option 1, if a times f of x is irreducible over f, then fx is irreducible over f. Option 2, if f of x plus a is irreducible over f, then f of x is irreducible over f. Option 3, if f of a times x is irreducible over f, then that implies fx is irreducible over f. This is the result about Eisentian criteria, and this type of result actually very important. Now I will say some application depends on this result. First example, consider fx equal to x square plus 1, which is member of Zx. Now I will see, is fx is irreducible over Q? For this, consider a equal to 1. Then f of x plus a, here I have considered it a equal to 1. Then f of x plus 1 equal to x plus 1 whole square plus 1. This is equal to x square plus 2x plus 1 plus 1. That means this is equal to x square plus 2x plus 2. Consider p equal to 2. Notice p divide 2 means 2 divide 2, also 2 divide, here this is an, this is a1 and this is a0. 2 divide 2 and 2 divide also 2, but 2 square does not divide 2 and 2 does not divide 1. So for this prime p equal to 2, this polynomial has satisfied the Eisentian criterion. Since has satisfied the Eisentiens criteria for p equal to 2, that means fx equal to x square plus 1 is irreducible over q. Okay. I hope my all viewers have understood why fx equal to x square plus 1 is irreducible over q. Our next example, I will see cyclotomic polynomial. I will see the function fx equal to 1 plus x square up to x to the power p minus 1. This equation is a irreducible polynomial over rational number when p is a prime number. Cyclotomic polynomial always irreducible over q, and this type of equation actually very important. How cyclotomic polynomial irreducible over q? Now I will see the proof. Write fx equal to x to the power p minus 1 over x minus 1. Then obviously x to the power p minus 1 means x minus 1 times 1 plus x square up to x to the power p minus 1 over x minus 1. Now omit this part. Then this would be 1 plus x square up to x to the power p minus 1. Okay, and this is actually this polynomial, and this is irreducible when p is a prime number. It's irreducible. Now consider a equal to 1. Then f of x plus 1 would be x plus 1 to the power p minus 1 over x plus 1 minus 1. Then this is equal to x plus 1 to the power p minus 1 over x. X plus 1 to the power p means pc0 times x to the power 0 1 plus pc1 x to the power 1 times 1 up to p to the power p minus 1 x to the power p minus 1 times 1 minus 1. I hope my all viewers have understood. Here pc0 means 1, x to the power 0 means also 1. Then this would be 1. pc1 means px. Up to here would be p into p minus 1 over 2x square, this type. Here minus 1, just cancel this part. Then this would be 1 over x px plus p into p minus 1 over 2x square up to so on. And when p is a prime number, for any prime p divide p into p minus 1 over 2. Similarly, p divide p into p minus 1 over p minus 1 times p minus 2 over 3 factorial. But p squared does not divide p and p does not divide 1. So obviously this polynomial f of x plus 1 is irreducible for any prime p. And since f of x plus 1 is irreducible for any prime p over rational number, so obviously f of x is irreducible over q. I hope my all viewers have understood. Now as for example, consider fx equal to 1 plus x square. Obviously this is cyclotomic polynomial for p equal to 3, and since p be a prime number, so obviously this is irreducible over q. Fx equal to 1 minus x plus x square minus x cube up to x to the power p minus 1. Obviously for any prime p, this is also irreducible over q. Why this is irreducible over q for any prime p? I have seen f of a times x. Seen the result, if f of a times x is a irreducible over the field, then fx is irreducible. Consider a equal to minus 1. Then f of minus x equal to 1 plus x square plus x cube up to x to the power p minus 1 for any prime p. And obviously this is cyclotomic polynomial. Of us know cyclotomic polynomial for any prime p always irreducible. Since this is irreducible, f of minus x is irreducible, so we can tell f of x is irreducible over q. I hope my all viewers have understood. I hope my all viewers have understood why I have told you cyclotomic polynomial is very important for any reducible irreducible test. Okay? Well, I will stop here. In my next video, I will discuss some more question, some more topic about this reducibility and irreducibility. Because I have told you many times, this type of concept actually very important for higher study. Okay? See you soon. Stay safe and stay positive always. And don't forget to subscribe my channel for more videos. Thank you so much.